Okay, my friends, and from your book 6.7, and which is the Simpsons rule, and 6.8, which is the other aspects of approximate integration, chapters, subchapters are omitted. Okay, so you will not be responsible from these subchapters. Okay, now today we can continue with the chapter 7. Okay. Applications of integration. And the first, the 7.1 subchapter, which is the volumes of solid of revolution. And in this subchapter, okay, and we will show how volumes of certain three-dimensional regions or solids, okay, can be expressed as definite integrals, and how can it be determined, okay. And we will not give a definition of volume, but will rely on our intuition and the experience with solid objects to provide enough insight for us as specify the volumes of certain simple solids, okay. And what I mean that, and please think about any rectangular object, okay, and we know that its area equals to length times width, okay, and after that we can calculate its volume by the length times width times height, okay. And for example, for the circle, okay, we have the diameter, and its volume will be pi r square, which is the area of the circle, and the times again height, okay. And volumes by slicing, okay, and we know the volume of a cylinder enables us to determine the volumes of some more general solids, okay, and we can divide solids into the slices by parallel planes, okay, and this is the idea, okay. And think of a loaf of sliced bread, okay. Think about a bread, okay. When you sliced some piece, okay, you will obtain, okay, lots of small area, and when you summation of all the slices, okay, you will obtain the whole volume, okay. And each slice, and after that, is approximately a cylinder of very small height. The height is the thickness of the slice, okay. And that means, let me sketch it on the coordinate system. And of course, this is a x, Okay, and my friends, that's the slicing. Okay, and it starts here, which is the A and B. A and B. Okay, and as you see, this cross-sectional area of each slice, we can determine its volume and sum these volumes to find the volume of the solid. Okay, and let's specific to this slicing. Okay, and on the coordinate system again. Okay, for example, the green slice area. This is the rectangular slice. Okay, and that means the xi minus xi minus 1. This point is, and that's the xi. Okay, and specifically can say the a of x. Okay, and the for a is less than or equal to x is less than or equal to b. Okay, and the a of x is continuous on that interval, and the delta xi equals to xi minus xi minus 1, and the delta yi, that means the volume. Okay, and the a of ci times, okay, delta xi, and the for some, okay, ci values, and the ci values here, okay, ci on or in, I'm sorry, xi minus 1 comma xi close interval. Then volume will be summation of I starts from 1 to the n, okay, delta vi equals to summation of a of c, I starts from 1 to the n, delta xi. Okay, and the volume V of a solid between x equals A and x equals B, having cross-sectional area A of x at position x is V equals to integral from A to the B A of x del x. Okay, and don't forget it, delta V approximately equals, okay, A of x times delta x, and the del V equals to, so that A of x times del x. Okay. Solids of revolution. And the many common solids have circular cross sections in planes perpendicular to some axis, okay, which is the y or x-axis, of course, and such solids are called solids of revolution, and because they can be generated by rotating a plane region about an axis in that plane, so that it sweeps out the solids. And for example, think about a solid ball is generated by rotating a half disk about the diameter of that half disk, okay, and the means, let me sketch it, okay, this is half disk, okay, let it, this axis is x, okay, when you rotate this half disk about the diameter of this half disk, okay, as you see, and you will obtain this three-dimensional, okay, ball, and it's the right angular triangle about one of its legs, okay, it can be, and so for example, again, let's talk about the right, I'm sorry, let's we have a right triangle like that, okay, as you see, and when you rotate it, a right triangle about the one of its leg, which is the, for example, this leg, okay, and the y on the y-axis leg, and you will obtain okay, and the solid right circular cone, okay, as you see, and if the region are bounded by the f of x and the y equals to, let me write the definition of it, okay? Are bounded by y equals to f of x, y equals 0, x equals a, and x equals b is rotated about the x-axis, then the cross section of the solid generated in the plane perpendicular to the x-axis at x is a circular disk of radius absolute f of x, and the area of this cross section is a of x equals to pi times f of x square. So the volume of the solid revolution is pi times integral from a to the b f of x square del x. Okay. And let's continue with the example. Question is, find the volume of a solid ball of radius a, and let's sketch it firstly. Okay. this is our ball, and this slicing, as you see, and the ball can be generated by rotating the half disk, okay, this blue half disk, and I can give its formula by the y equals to, okay, square root of, because this point is a, okay, and the a square minus x square, we know that, okay, and the x square plus y square equals to a square, okay, and which is the hypotenuse, and let me continue with the y equals that, so it's, okay, rotating on the x-axis, okay, that means this half disk, which is it is, okay, rotating, and the minus a is less than or equal to x is less than or equal to plus a, okay, it's on about the x-axis, and as you see, this is the cutaway, which is the blue okay, half disk, and the sorry, volume equals to, okay, pi times integral, okay, from minus a to the plus a. This is the minus a, okay, of course this is plus a, and the integral square root of a square minus x square, because of the, it was the, from the theorem, okay, f of x square it was, so del x, okay, and it equals to, this is the even function, so 2 pi integral from 0 to the a, okay, and a square minus x square del x, and it equals to 2 pi times, okay, and the a square x minus x cube over 3 from 0 to the a, okay, and it's equal to 2 pi times, okay, and the a cube minus 1 over 3 a cube, okay, and it equals to 2 pi times, okay, and the 2 over 3 a cube, so it's equal to 4 pi a cube over 3 cubic units. Okay, and the example, now the right circular cone, and the find the volume of the cone of base radius r and height h, that is generated by rotating the triangle with vertices zero point zero, h point h comma 0 and h comma r about the x-axis. Okay, let's firstly select these values, okay, and the maybe set the z, sorry, yes, this one is true now, x, y, z, okay, and the points are here 0.0, right, and this is h comma 0 point, this point is, okay, h comma r. As you see, we have a triangle now, right? Let's connect these 3 points to each other. Yes, we have just evaluated this right triangle, okay, and when you rotate this right triangle on the x-axis, okay, and you will obtain like this cone, okay, and for here, I'm sorry, what can you say for this line, okay, s equal to y equals to, okay, rx over h, okay, yes, because of this point is h, this point is r, and the rx over h for the any value, okay, and after that everything is easy to calculating the total volume of this solids, okay, integral from 0 to the h, okay, and the y square, what was rx over h square lx, okay, and it's equal to, okay, pi times, okay, r over h square, okay, and the x cube over 3 from 0 to the h, so it's equal to 1 over 3 pi, okay, and the r square h unit cube, okay.